that I have here. So before we begin, let me tell you a little bit about how I structured this entire talk. Even before that, Devashish, how much time is this? Is usually what is the duration of this sort of talks in your math club? Could you tell me?
Sir, 1 hour.
1 hour. Okay, that's great. So, the way I structured it is like this. First, we will talk a little bit about the motivation of this particular problem. So I will be talking about one problem in mathematics that I could solve with the help of my advisor, my doctoral advisor, Professor Chris Rushka. So I'll talk about the problem, and then I will put certain things together that you can use to further your understanding. And that is the main goal of this particular talk, that you, at the end of this 60 minutes discussion, have some usable elements that you can then use to further your own work and learn more and whatnot. Okay, so first comes the motivation, why we are here and what is the thing that we want to learn. So this is, as I said, it's a joint work with Professor Chris Rushka. It was done mostly in University of Wisconsin, Milwaukee, though the last part of the work was done in Calcutta, which was a further generalization of the main result. So I'll first talk very briefly about the main result that we have. Now, I must warn you that many of you may not understand all the words in the sentences that I put here, but that is all right. In a short amount of time, we will cover some of the grounds so that you can understand these words. But here is the big picture, that there is a very big name in the field of geometric group theory, the field that I work in. His name is Brian Bowditch. You can Google him. He has fantastic expositions of geometric group theory as well. So Bowditch made a conjecture in the year 1997. So this is the paper. Maybe I can use this. Okay. So here is the paper. The name of the paper is here. So he made a conjecture. And what was the conjecture? He said that boundary of a large class of groups is locally connected. It's a very loosely stated conjecture. I'm not exactly using Bowditch's word, but this was the main content of his statements. And there are certain words here that, of course, I have not yet explained. Like there is the word boundary, there is a word group, and then local connectedness is there. So bunch of words that make up this sentence. But nevertheless, he made this conjecture that boundary of a large class of groups is locally connected, and that large class of groups that he was working with was the one-ended relatively hyperbolic groups. When I say large class of groups, I'm actually referring to this collection of groups. Whatever this means, of course, I have not explained what that means, but this large class of groups called one-ended relatively hyperbolic groups, you can define something called boundary of those groups, and then you can show that these boundaries are locally connected. If you have seen a little bit of topology, then you know that local connectedness is a very important property of a topological space. In a sense, if you look very closely at a point, there aren't too many breaks or divisions or something like that. So you can look up local connectedness. I will not define what is local connectedness in this particular talk. If you don't know what it is, you can look this up. In any standard topology book, you will have local connectedness, and it's a very important property of a topological space. If we know that a certain space is locally connected, we can immediately say a lot of things, a lot of good things, nice properties of that particular space. So this property is a highly desirable property of a topological space. And Bowditch conjectured that boundary of these relatively hyperbolic groups, one-ended relatively hyperbolic groups, are locally connected. And what happened is he proved this partially with a lot of restrictions in the hypothesis of his theorem. So he did not prove it for all relatively hyperbolic groups. He proved it for a certain special set of relatively hyperbolic groups. So a complete solution of this conjecture is available in my doctoral thesis. I'll put a link, you can check it out. And in 2020, this was made available in the public domain. And then a further generalization of it in the infinitely generated case is also in preparation. I think it's a joint work with Chris Rushka. Again, you can probably find it in archive by the end of this year. We are just tweaking the final parts of that particular paper. But the finitely generated case is already available. The finitely generated case, which is in fact a large chunk of the work, it's most of the work actually, that's already available and you can check it online if you want. Now, so we have this result that boundary of a certain class of groups is locally connected, and this actually there is some evidence that there is this result is very useful in furthering investigation of these boundaries. And in fact, we already have some citations. Some of the researchers, for example, Michael Mahalik and Matthew Hallmark from Vanderbilt University, have already used it in 2021, this result that we had in 2020. And another paper which Chris Rushka, my advisor, did with Matt Hallmark, the same result was also used to understand the boundaries a little bit better. So far, we have established a little bit motivation behind what we are studying today. That a particular space, which is known as a boundary of a group, is locally connected. And there is some evidence that this particular space is in fact related with a large class of groups called relatively hyperbolic groups. Okay, so now let me put this a little bit more clearly here. Bowditch boundary, that's the first set of words that I referred to. One-endedness, I talked about this particular word as well. Relatively hyperbolic groups, I said this as well. And I talked about local connectedness. All of these unknown words. We will now get into discussing what all of these things mean and a little bit of intuition behind how we can understand the big picture. Okay. So feel free to post questions in the chat if you have any. Interrupt me, that's fine. Now, all of these things actually, in fact, a large chunk of work in geometric group theory, that actually can be traced back to the work of Michael Gromov. In fact, if you guys are looking at this particular topic for the first time, I will strongly recommend that if you don't remember anything out of this seminar. Just remember this, the name of this particular paper, hyperbolic groups. This was published in 1987. It was written by Misha Gromov. And what he did in this paper, this was like he posed 10,000 questions that researchers can work on. And then they worked on that for the next 30, 40 years and still working on that now. It's a very, very well cited paper by Gromov, and you can definitely find it in the internet. Okay. Now, so he talked about a variety of ideas in that paper. Two ideas that will be useful for what we have today are hyperbolic groups and then we will add another adjective to it called relatively hyperbolic groups. So one more adjective to this setting. And if you have even a little bit of background in differential geometry, you or in any geometry, in fact, you have probably heard about hyperbolic, the word hyperbolic geometry, negative curvature. These things come up in geometry all the time. Gromov's big idea was that you can understand these concepts, the concept of hyperbolicity, even in the context of algebraic structures like groups. And it's quite wonderful, and we will learn what that means today. How can we think about a completely geometric, in some sense, a completely geometric intuitive structure called negative curvature and hyperbolicity in the context of a completely algebraic object like a group? It's quite beautiful, and we will talk a little bit about it. But first, let's get into the philosophy of geometric group theory. What is the underlying philosophy of it? And it's very simple actually. What you want to do is, you want to discover algebraic properties of a group. That's what you want to do. And how do you do it? Well, you use the action of that group on some suitable topological space. You see how the group is acting on a topological space, and using that action, you want to understand the algebraic properties of the underlying group. So that's what we will be doing today. We will analyze some spaces, which is in the domain of topology. We will be able to discover some properties of the group, which is part of group theory. That's the big picture story, okay? You take a group, you discover a space on which the group acts, you study that space, the properties of that space gives up properties of the group. That's the big picture story, okay? So I'll give you one example which will let us understand a lot of these ideas and understand some of the words. So this particular result was known to Efremovich, Schwartz, and Milnor in the 1960s. I don't have the precise dates of the papers because of a couple of reasons. A couple of these people are Soviet mathematicians, I think, and the paper publication dates are kind of jari at there. And Milnor's publication was probably later than Schwartz, but independently discovered. So this is a very important result in geometric group theory. And what it says is something very remarkable. It says you take a group, take any particular group that is acting in a certain way, properly discontinuously and co-compactly. We will understand what that means. The group is acting in a certain way on a topological space. Suppose this happens. Then Efremovich, Schwartz, and Milnor says that the group looks similar from a great distance. So notice that I have put some of these words in bold, that it looks similar. What does that mean? From a great distance, what does that even mean? Okay. But intuitively speaking, if we can sort of see the group in the space, if we can sort of see the group in the space, then that can help us to understand the group by using the space. We will precisely understand what this means using one example. Okay, so let's look at this example and we will immediately understand a bunch of these words: group, topological space, action, properly discontinuous, and co-compact. Let's see how does that work. So we have a space, or you can say a topological space. Let's take the real line. So you have the number 0 here, 1, 2, -1, -2, and so on. Okay, and maybe you have 0.5 here, you have 4.2 here, and all of those numbers are all sort of marked on this line. You can think of it like that. So this is definitely a topological space. So this real line is an example of a topological space. So now you may want to know what is a topological space and what are its precise definition. I will not go into that, but you can imagine this as a set. Of course, the real line is a set of points. It's a set with a preferred collection of subsets, a preferred collection of subsets. So we take the real line, we take the line means we take all the set of all the points on the line, and then we say these subsets of the real line are my preferred collection. These subsets of real line. Okay, so I don't know. Can you mute participants? Someone? Yeah. Thank you. If you're not speaking, please keep yourself muted. Thank you. All right. So that's an example of the topological space that we will be working with. Now let's look at a group that is acting on this topological space. So our example of a group Z, is precisely the integers. And so on. Okay. So first we had an example of a topological space. It is a set with a preferred collection of subsets. Now we have examples of a group. Now let me quickly tell you what that means. Notice that if you combine any two elements of Z by addition, you get another element of Z, right? If you add two integers, you get another integer. It's very simple. There is another property of this set Z. Well, I should actually write Z comma plus because I'm thinking about this addition operation as well. So there is another principle that if you take a number, I can give you another number that is the inverse of it. And you exactly know what is inverse. The inverse of what? If I ask you what is the inverse of 2, you can almost by reflection tell me it's -2. Even without pondering over what its definition is. Well, what is its definition? Well, if you add a number and its inverse, you get the zero element. But I have not told you what is the zero element. Well, you exactly know what it is. A zero element is something which, when added to anything else, gives that element back. Okay, so all of these properties together make a group. And there are some other properties like associativeness and so on. I'm not going into that. So we have, so maybe I can do one thing. I will just add a page here. Not sure if I can. Okay, here we go. So a quick review. So we said that G or Z is a group because I can add its elements and get another element of the group of the set. I can find inverses of each element. Okay. For 2, it's -2. There is a zero element. There is a zero element which, when added to other stuff, when added to other elements, does nothing. I mean, you get that element back in some sense. And then there are certain other residual properties like associativeness and so on. You can check this up in your standard algebra book. So now we have a group and a topological space. Next thing that we want is the action of the group on the topological space. What does that even mean? Well, it's actually quite simple. We can think of each element of the group as a function defined on the space. Let me write that. Each element of the group can be regarded as a function from the space to itself. So, for example, I can take the group element 2. 2 is a group element, right? 2 is a member of the set Z with all those properties. Z comma plus I can write maybe. What I can do is I can think of this number 2 as a function from R to R. How do I think about it like that? Well, I take any member X in R and I apply the function 2 on it. And can anyone guess what is the output? If I apply the function 2 on the point X in R, can anyone guess what output I have in mind? Maybe you can type it in the chat or you can speak up if you want. Where will be X sent if I am applying 2 on this particular element? Okay, yeah, of course. X plus 2, thank you. That is correct. X will be sent to X plus 2. So it's very simple. We are just, when I'm saying that this element A is acting on real line, I am thinking about this element A as a function of this real line. And what I'm doing is I am just shifting each member of real line by A amount. So it's just addition by A. Okay. So we now know what is precisely group action on a topological space. And what is it? It is a way of thinking. Well, in this case, we are actually precisely thinking of translation. So it will be continuous. Yes. Actually, Aditya is right. I mean, we can say a little bit more what kind of functions that we are looking at. In fact, we can also ask that if I have two different group elements, do I think of them as different functions? If I take two different group elements, are there, each of them is a function on R2R. Okay, I understand that. But are they the same function or could they be different functions? So in our context, each number will define a unique translation. If you take the number 3.4 and if you take the number 2.3, they will not be the same function. But there could be cases where two group elements are actually giving you the same function. So I'm not going into that detail because I'm kind of, well, that's not the whole point, I guess. But the group action, the only thing that you need to remember as an intuition is the following. It is a way of thinking elements of the group as functions from the space to itself. So this is the sort of a way I think about group action actually. For precise definitions, again, look up books. All right, so we have this. We understand what is the third word, which is action. Now we need properly discontinuous. Well, that's quite a big word. What is the meaning of properly discontinuous? Okay, so let me add a page here. It's actually quite simple. Properly discontinuous. So what you do is you can go if you want. Okay. You take a bounded set. So let's take a bounded set. So suppose this is my real number. Okay. I take a point. I take a little set here. Let's say I take a little set here. Let's say I take 0 to 1, all of the members. Why not? Let's do that. So what I'm going to do is I will apply the function 3. Remember, each member of Z is a function on the real line. So I will be applying the function 3 on this closed interval. So applying the function 3 on closed interval 0 to 1. So I want to know what is in the intersection of 0, 1 closed interval with 3 applied on 0, 1 closed interval. So can anyone tell me what is that intersection? If I apply the function 3 on the 0, 1 closed interval and I try to see what is the stuff that is common between the input and the output, what is it that is common here? So where will 0 go under this map? Where will the point 0 go under the map 3? Well, 0 will go to 0 plus 3. Excellent, very nice. And 1 will go to 1 plus 3. So that's 4. Now, what is common between the input? The input intersection is a null set. Excellent, Udita. That's correct. So this intersection is phi. So that is sort of the ideal scenario. That is sort of the ideal scenario that we want. Okay, yeah, of course. So now if we want this particular thing to happen, we sort of formalize this thing. And let me write down the precise definition of, let's see, properly discontinuous. Okay, so if we can say that, let's take all those group elements Z in the group, this is the group, and suppose K is a finite set. K is a finite, actually let's in fact make it better. K is a, instead of saying finite interval, I'll say K is a compact, K is a compact set. Now, is it possible that K intersection GK is not equal to the empty set? Is that possible? Well, let's look at this. So if my K here is 0 to 1, this is my K, the compact set. I want to know that if I hit it by a group element, so I get GK, the intersection of K and GK is not empty. Well, you can sort of imagine that it will not be empty for only, okay, for G equal to 0, yeah. What else? Apart from G equal to 0, what else will work?
G minus 1.
G equal to minus 1 will work, because if you slide it 1 unit to the left, the 0 point, there will be 1 point in common, okay? And if I put it as 0, okay, as Shivam Kundu is right, it's 1. Remember, we are only dealing with integers. We are not seeing the action of real numbers on real numbers. We are seeing the action of integers on real numbers, okay? So you have 0, minus 1, and 1. Only 3 integers are there, or 3 group elements are there, such that K intersection GK is not phi. There are only 3 group elements such that 0, 1 intersection G01 is not phi. So in fact, the action is properly discontinuous if this set is finite. We got three group elements for this particular compact set. 3 group elements for this particular compact set. If I take any other compact set, like let's say a bounded interval or something, then we will get some other number of group elements. But as long as the number of such group elements is finite, we can say that the action is properly discontinuous. So that is the fourth word here. In short, most of the group elements is moving compact sets disjointly from the original set. Thinking about infinite groups, if I think about infinite groups, then most group elements will actually displace a compact set. This is how I think about it. There is a definition and there is one thing how I think about it. The group elements are moving the compact sets because they are functions from the set real line to real line. I want to know, are they moving them enough And the question is, if most of them are moving them disjointly from the input set, then we say that the function is properly discontinuous. The action is properly discontinuous. Okay, one last word, co-compact. Okay, so what is co-compact? Well, if you have learnt about quotient of group action, then we want this particular thing to be compact. If the quotient is compact, then we say that the function is the action is co-compact. But we will not be using this very much, so I will not say more on this. We're almost running out of time. So let's get back to the statement that we were making earlier. Now we sort of understand a bunch of these words. We say that, okay, a group is acting on a topological space. So you think about integers acting on real line, and the action is properly discontinuous. Compact sets are mostly moved disjointly from each other, from the image, from the input interval, and co-compactly that happens. So we sort of understand what of this, most of these words. Then Efremovich, Schwartz, and Milnor says that the group looks similar to the space from a great distance. Now we will exactly know what it means. Let's see that quickly. If I draw a picture, let's move it a little bit downstairs, maybe like this. If I draw the real line, this is the space. Now we have the group. What is the group? The group is 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on. If we mark these on the, well, in this particular example, I set up this example in a way that it's easy for me to mark it actually. So I can mark 0 at 0. So this point 0 is not only a point of this space, I can use this vertex to think of this element of the group. Then I mark 1, I mark 2, I mark -1, I mark -2, etc. Okay, so this example is actually very suitable to understand what's going on, but there is something going on under the hood, so I have not talked about that. I'll speak about that in a moment. So now what I'm saying is, think about these dots. These dots, each dot is a group element. So each dot is a group element from Z. Now I will connect these dots using some rules. Connect the dots by edges using some rule. I'll tell you what the rule is, maybe if I have time. So I can just connect it like this. This is one way to connect the dots. There are multiple ways of connecting the dots. So let me warn you. Warning. Multiple ways are there. Multiple ways are there to connect the dots. So once you connect the dots like this, I'm just connecting every member. So if A is a member, if A is a dot, I'm just connecting A with A plus 1. Why I am doing that? Because by just adding 1, and of course I'm also connecting with A minus 1. So why am I doing that? Because by just adding 1 and subtracting 1 from every member, I can actually reach all the members in the set. Starting from just 1, and just by adding 1 and subtracting 1 as many times as I want, I can create the entire group. That's why I'm choosing 1 here, but I could have chosen something else as well. Now, if you look at it from a distance, what are we looking at? One is the real line. The other thing is this thing that you just created. What is the thing? One dot for each group element connected by edges. One dot for each group element connected by edges using some rule. If you look at both of these objects from a great distance, they will look exactly the same. In fact, even if you, well, we are actually working with discrete groups in some sense. The properly discontinuous action ensures, is actually enforcing some sort of a discreteness on this entire group. So for the moment, we're not thinking like Lie group or anything, okay? Just thinking about discrete groups. In fact, you can say finitely generated groups as well, okay? Okay, so now we sort of know how a group looks like. Those of you have seen this, I'm actually talking about the Cayley graph of the group. So what I just said and what this particular theorem by Efremovich, Schwartz and Milnor says is the group looks similar, means the Cayley graph of the group, looks similar to the space from a great distance. So there is a concept of quasi-isometry which makes this looking from a great distance idea precise. I will not go into that, but if you look into this picture, the main story becomes very clear. What you do is you look at the real line and then you create the Cayley graph of the group, just like I told you. Put a dot for every group element, join the edges by using the generating set, using some rule. Then looking at the Cayley graph and looking at the space from a great distance, you cannot tell them apart. That will not happen always. That will only happen if the group acts properly, discontinuously, and co-compactly on the topological space. That's the key idea that Efremovich, Schwartz, and Milnor discovered, that if a group is acting in this beautiful way on the topological space, then if you look at the Cayley graph and if you look at the space on which the group is acting from a great distance, you will not be able to tell them apart. Okay, so this brings us to the final leg of our discussion, that now that we understand what it means to have a group acting on a space, we can actually talk about the boundary of the space, which is the basic idea that we will be talking about, that is boundary of the group. So what is it about? Okay, so we have this setting that a group gamma is acting on a space X. This is a group, it's acting on a space X, topological space X, that is delta hyperbolic. So we'll spend a couple of minutes to understand what this means. How can a topological space, what is the meaning of delta hyperbolicity in a topological space, in a metric space, in fact. So let's look at a picture here. It's a very simple idea that we will be discussing, it will take just a minute to understand. If you have studied differential geometry, Gaussian curvature, and all of this very beautiful stuff, you probably have heard about negative curvature. Even if you have not thought about negative curvature, you must have seen a piece of paper, the top of a piece of paper, and thought, oh, this is flat. This is not curved. This has zero curvature. Maybe you have thought about that. And then when you sort of bundled the paper a little bit, you said, oh, now it is curved at some places. So there is a notion of curvature that geometers like to study a lot. And one way to talk about this curvature is using this beautiful idea that Gromov introduced. This is the notion of thin triangles. So this sort of generalizes the notion of curvature that we already have. So what is it? It says, okay, do you want to know whether x is delta hyperbolic? In a sense, delta negatively curved. What does it even mean? Well, take any 3 points on your space, A, B, C. Let's take any 3 points, A, B, C on the space. Join AB, like with the shortest path, like a geodesic path from A to B. Join AC and take a neighborhood of AB and a neighborhood of AC. So take a pipe about a sort of tubular region around AB and a tubular region around AC. Take the union of these two tubular regions. You will see the third side of the triangle is contained within these tubular regions. The third side is contained between the delta in the union of the delta neighborhoods of the other two sides, AB and AC. You can check that this will not work in the normal XY plane. This is not delta hyperbolic. What does that mean? That is, if you take any 3 points, you have to fix delta first. Maybe delta is 2.1. I don't know, some number. You cannot, it is not true for every triangle that if you take a 2.1 neighborhood of one side and a 2.1 neighborhood of the other side, the entirety of the third side will be contained by it in that union. If you take a 2 point, you cannot change this delta. You can make the triangle as large as you want, but you cannot change the delta. That's the condition of the definition. This thing and this thing, you can easily set up a triangle like this. The hypotenuse in this particular case is not entirely contained in the union of these two rectangles. Well, it will be actually not like rectangle, it will be like something like this maybe. Okay. So you can set it up, you can make a big enough right angle triangle and you see easily that it doesn't work. So if a space admits such a delta, that is for every triangle this works, delta neighborhood of union of delta neighborhood of two sides contains the third side, then we say that particular space is delta hyperbolic. That's a hyperbolic space. Okay. So what we say is that if a group gamma is acting on a space X, a topological space X, that is delta hyperbolic, in a nice way, the nice way means it's properly discontinuous. Actually, the action is properly discontinuous. If you have that, then you can define something called the boundary of the group. And this is a very, it's one of the stunning ideas. Here is the intuition. What you do is, you take the space X, okay? You take any point X naught. So fix a point X naught. And you look at all the geodesic rays that are running off to infinity. So like this. You take, these are all rays emanating from X naught. These are rays emanating from X naught. Geodesic rays, in fact. Geodesic rays. Okay. So what you do is, now this requires a little bit of imagination. The way I think about it is like this. Every time I find a road that is moving off to infinity, every time I find a road that is moving off to infinity, that is a point at infinity. That defines a point at infinity. So every road that is moving off to infinity can be thought of as a point in the boundary of the space or a space at infinity. Think about it. So it's a very beautiful idea, and here is how I define the boundary. It's a boundary collection of roads winding off to infinity. I mean, I'm saying this very roughly. You can see it, what I'm saying, but it's exactly what it is. It's nothing more, nothing less. There is certain equivalence relations that you have to apply and certain things that you have to say, but roughly speaking, this is what it is. You look at the boundary of the space X on which the group acts in a beautiful way, and the space itself is delta hyperbolic. You look at the collection of all the roads that are winding off to infinity, and that itself creates a space called the boundary of the group. One can show that this is well defined, in fact, for a particular group. And we try to show that this particular space, the boundary space, is in fact locally connected. This was conjectured by Bowditch about 20 to 25 years ago. And in the finitely generated case, we could show that the boundary, that is a collection of roads that are winding off to infinity, that collection of roads is actually a topological space that is locally connected, and it has many nice properties. Okay, so I will be stopping here and I'll be open to taking questions. Thank you. So if you have any questions, you can unmute yourself and say it. Okay, so here's a question. Technical need of nice action to, oh, yeah, so if the group is not properly discontinuous, if the action is not properly discontinuous, we cannot actually, and if it doesn't have that, I mean, we are not actually asking for co-compactness in the entire space. So we're just thinking about properly discontinuous actions of the delta hyperbolic space. If we don't have that, then very broadly speaking, the group will not look like the space from a great distance. That's the technical requirement. So we will not be able to establish a quasi-isometry of the group with the space. And that makes the entire thing possible, actually.
Yeah. I have one question. That is, I'm saying, so basically you are saying given a group, you can construct, say, a calligraph, right? When you are taking
any group, we can construct a calligraph. Yes.
Okay, so I'm saying that then the quasi-isomorphism between what? Between this calligraph and the space? Are you saying? I mean,
yeah, Exactly. There are many Cayley graphs that you can draw for a given group. If you just
Okay.
change the generating set,
Mhm.
you can actually construct several types of Cayley graphs of the given group. It can be shown that if the group acts properly discontinuously
Okay.
and co-compactly on a particular space, then the space itself is quasi-isometric with the Cayley
This.
graph of the group. Any Cayley graph, any Cayley graph.
Okay. Another question, that is this quasi isomorphism I only encountered in the context of this chain complexes. So is it like some kind of chain complexes, then the isomorphisms are quasi isomorphism? Is it some notions of chain complex comes here?
No, actually quasi-isometry, I'm saying, okay, maybe I can write it here. Quasi-isometry. So what it roughly means is, so if it's isometry, suppose a function f from x to y, it is isometry
Oh,
if
sorry, isometry. I thought isomorphism. Sorry, yeah. Okay.
if distance of x1, x2 inside x and distance of fx1, fx2, fx1, fx2 inside y, if these are same, then it becomes it's isometry.
Okay.
It's quasi-isometry if we can sort of wiggle it a little bit. That means we can put a constant here and a constant here and bound it by that.
Okay.
So the distance is not exactly preserved.
Hmm.
The distance is not exactly preserved. I mean, there is a lower bound actually. You can use the same numbers, but you can use different numbers as well. So the distance are not exactly preserved, but they're preserved up to some bound. That's the notion of quasi-isometry.
Okay.
And if the action is this has these properties that it's properly discontinuous and co-compact, then this Cayley graph becomes quasi-isometric with the space on which it acts, the group acts.
Can it happen that say there are two non-isomorphic groups, but they are producing,
Isomorphic groups, yes, of course.
but they are producing the same, I mean, Cayley graph says that they're isomorphic to the same space. I mean, can it happen? They're non-two isomorphic. Then in that case, I'm saying it is not giving that much information about the
It
group.
is not actually, no. There are certain limitations of, so if two groups are quasi-isomorphic, it is not clear if they are the same group. It's a good question.
Okay.
But they will have certain properties which are remarkable. For example, which will be same. For example, if one of them quasi-isometric, I'm just saying quasi-isomorphic every time. So one of them, if it doesn't have a splitting over finite groups, then we can say that the other will not also have a splitting over finite groups. So for example, if you want to have a graph of group decomposition of that particular group, then many of the properties of both of these groups will be similar if they're quasi-isometric.
Okay, so the examples you provide, this f x to y, it's a space or groups? That time I did not focus them.
These are topological space actually, but you can actually think about this x as delta, which is the Cayley graph of the group.
Okay, okay.
And you can think about the Cayley graph as a topological space as well. Just the realization of the Cayley graph. You can think about each edge as one.
So in that way, I can talk about quasi-isomorphism between two groups.
Exactly.
Okay.
Great questions. Thank you.
Okay, thanks.
Okay. Next question. Anyone else? Unmute yourself, and if you want to speak up, that would be great. Okay, I think not then. Any, Devashish, should we conclude it now then?
Yeah, another question.
Oh, yeah, please go ahead.
So basically I'm saying that in the other direction, can we say anything? Like, for example, say two topological spaces are say homotopy or something. and then can we say something in the other direction?
So if two topological spaces are homotopic,
Yes.
are they quasi-isometric? I think you can probably, I have to check that actually.
Okay.
Maybe yes. Yeah.
Because if it is homotopic, then it is a very good in the sense it's a similar, like for the example, like most of these invariants are homotopical invariants, like homology.
Yeah.
So
Yeah.
that's why.
Yeah. So you can actually talk about fundamental groups, and you can compare them and so on and so forth. Yes.
Okay.
Any other questions? Okay, so thank you for having me, Devashish. You want to conclude the
Yeah.
session, or should
Yeah.
I?
Yes, sir. On the behalf of Whole Mathematics Club, I would like to say a great thanks for this amazing talk, sir. Thank you for taking out some time out of your busy schedule and giving that to us. We really enjoyed the session, and it's definitely helpful to most of the students here. A great thanks for coming, sir.
Thank you. Thank you. Thank you very much. Thank you. Bye, everyone.
Yeah.